Yeah, so as Kayla said, my name is Sarah Madigan, and today I'm going to be talking about the power grid. So just a brief introduction about myself. I'm a sophomore at Ohio State. I'm studying electrical engineering. And my internship experience, I've actually worked for Burns& McDonnell for 2 summers. The first summer I was in the substation department, and the second summer I was in networks integration and automation. And those two internships are what inspired me to give this talk, just because I learned a lot about different aspects of the power grid throughout the time I was there. I'm actually currently on co-op with GE Appliances. I'm working in laundry electronics. In the summer, I'll be in the manufacturing department at Texas Instruments. So just going to go over a quick agenda for this talk. I'm going to talk about the major steps in power transmission. So this is how power gets from generation sites to your home. So we're going to go over generation, transmission, substations, and distribution. And then I'm going to talk a little bit about how the power grid looks geographically and how energy is sold to different consumers. And then I'm going to just elaborate a little bit on different careers in power engineering by major. So the first thing I want to talk about, just give a very high level overview of the major steps and, like I said, how power gets from those large scale generation sites to consumers. So the first step is generation, and that's just like the typical power plant you'd think. A lot of them run on fossil fuels. There's a lot of different types of power generation. And then after that comes power transmission. So those are the very large, super high above the ground power lines that you'll see just spanning very, very large areas. And then after transmission comes distribution. And distribution lines are a lot smaller. They're a lot lower to the ground than transmission lines. And those are something you'll see in your neighborhood, maybe if you have above ground power in your neighborhood. And then after distribution, then we come to the end use. And that's just like the power you get out of your wall inside your house. So I'm going to start by talking a little bit about power generation. So I want to talk about the major sources of power that the United States uses. Unfortunately, we still rely primarily on fossil fuels for our power. And there's been a shift recently, obviously, to try to change to more renewable energy sources. So as you can see in this pie chart, renewable energy currently makes up about 11% of our power sources. We're obviously striving to increase that just as we're becoming more environmentally cautious. So of that 11% that's renewable energy, 43% is by burning biomass. And then about 24% is by wind turbines, 22% is by hydroelectric power, which is essentially when water in a dam just spins a big turbine and you get your power that way. Also, about 8% of our power is nuclear electric power, and that's basically nuclear fission, a process that occurs in nuclear power plants. And that is a bit environmentally dangerous. So that's another power source that people are trying to transition away from if possible. So after generation, usually you have what's called a step-up transformer that's directly outside of the generation site. And that step-up transformer is going to bring your power to an extremely high voltage. We're talking about 69,000 to 765,000 volts. That's very high. Just for reference, the power you get out of your wall is about 120 volts. So we're talking like very large voltage. And you can see the image on the right shows different voltages of certain transmission structures. So the three on the right will be, those can be most accurately categorized as power transmission. And you can see those are very large structures, very tall. And the two on the left side, those are more focused on distribution, which I'll be talking about a bit later. But yeah, so the reason that the three transmission lines on the right are so high up is because they, like I said, they're transmitting power at extremely high voltages, and there's a lot of safety concerns surrounding that. You do not want to be touching 765 kV. If you're anywhere near the ground, then you will get electrocuted. And also those power lines at such high voltages generate electromagnetic fields. So that's something that people don't really want to be close to, obviously. And it's currently estimated that we have about 163,000 miles of transmission lines in the United States. So we have a very large network. And there's different classifications for what exactly falls under power transmission versus distribution. But that 163 mile statistic, or 163,000 mile statistic, is just 230 kV to 765 kV. So yeah, we're talking very, very large scale equipment, very high voltages, not something you want to mess around with. It's also important to realize that this power is AC power, so that just means alternating current. So instead of just getting a constant value of current, you're actually having it have the shape of a sinusoid graph. That's just like a little bit more optimal of a way to transmit power over large distances and to lots of different consumers. And one analogy that I like to use when I'm talking about transmission versus distribution is power transmission is like the interstate highway system. And I just pulled these two images online. Essentially, so the one on the left, that just shows all of the major transmission lines in the United States. And the one on the right shows the interstate highway system in the United States. Now it's important I got to acknowledge there's not like an actual official correlation between the two. So there's not like a rule saying, oh, you have to transmit power along highways. I just thought it would be interesting to look at the comparison between the two. There does appear to be, like you see the area on the eastern United States that has more freeways closer together. There's a lot more power lines there just because it's more highly populated. And then you go out west and you get a lot less densely populated. So yeah, I just thought that was an interesting analogy. And that'll make more sense when we talk about power distribution, because power distribution can be referred or can be thought of as just like those smaller neighborhood type roads. So I'm going to talk now just a little bit about why we're transmitting power at such high voltages, right? Like I talked about how dangerous those voltages are. They're not really something you want to be messing around with. But one of the reasons we do that, actually the primary reason, is our goal is to minimize losses on the power line. So power losses are essentially just wasted power. So imagine if you generate 100 units of power and 20 of them are lost, you just wasted all that natural resources you used to generate that power, and the power company is losing a lot of money in that. So we really want to engineer our systems so that they reduce the amount of power losses. And I just have a little bit of math here showing exactly what's going on when we're having such high voltages. So you can see the top equation, that's just, for those of you who took Physics 1251, that's just your basic power equation. So the total power generated by a system is equal to the current times the voltage, or current equals power over voltage. And so the bottom equation shows the power losses. So you just have power equals I squared R, another just basic physics equation from Physics 1251. And then we can actually substitute the two equations into each other. So what I'm doing is just substituting total power over voltage for current and squaring it like it's squared in the equation. And we can see that power loss is actually equal to the total power squared times the resistance of the line over the square of the voltage. And that brings us to our proportionality relationship, showing that the power lost on the line is inversely proportional to the square of the voltage, which means that higher voltage is going to have a lot lower power losses on the lines, which is super important because we don't really have a whole lot of control over the resistance of the line. Like you can use different material, but at the end of the day, the voltage is what you really can control most easily. So that's why we mess around with such high voltages on power transmission. Like if we were trying to transmit 120 volts over a distance of like 300 miles, the losses would be insane and you would essentially not even be getting power just because the voltage is so low. Excuse me, and the losses would be so great. So yeah, that's a bit of a mathematical explanation of why we're trying to change those voltages. And so how we do that is we use something called a substation. And a substation is essentially a yard of equipment, and the main purpose of it is to, like I said, change that voltage from high to low. So I'm just going to go over here some major equipment that's in substations. I know that like there's tons of other elements of substations. I could not possibly cover them all just in this 20-minute presentation. So I'm going to go over the major ones. On the left, you have a circuit breaker, and a circuit breaker essentially is like, it's almost can be thought of as like a sort of large switch that allows you to isolate different parts of the substation. For example, if you're trying to do maintenance on them and you have like a line at 200 kV, you do not want to be touching that 200 kV. So you can actually manually flip the switch on the circuit breaker and it'll open the circuit. So you'll just have like an open circuit in the middle of your substation. You can safely do work on it, touch whatever you want. And circuit breakers are also used for if there's a fault, such as a large spike in current or voltage, the circuit breaker will automatically trip and isolate as much of the substation as possible to prevent against damaging the equipment. And one of the reasons why preventing against that damage is so important is you have your transformers, like the middle image shows. And this was actually shocking to me when I learned this for the first time, but the transformers in a substation they could be worth upwards of $1 million. So they are super expensive. You do not want to mess with having your transformer be blown out by a fault. So yeah, we're really trying to protect the transformer with those circuit breakers. And basically what the transformer does is it's the part of the substation that actually does the stepping up and stepping down of the voltage. So depending on the turn ratio of the coil inside of the transformer, that's by how much the voltage is going to be changed. But yeah, so the transformer is basically like the heart of the substation. It is the most important part. Without a transformer, the substation isn't even really doing, like it's not even changing the voltage. So yeah, very important there. We want to protect it at all costs. That's why we also have this piece of equipment called lightning arresters. You can see them, the image on the right. They're usually located at a pretty high elevation in the substation just so they can protect against surges that are caused by lightning strikes. Again, we're really trying to protect the transformer, prevent against fires and that kind of thing with that. And like I said, there's tons of other equipment that's found in a substation, but those are three of the most important parts. And this image here actually shows a very large substation site. Usually they're a little bit smaller than this. This one has a lot going on at it, but you can kind of see, you can see the circuit breaker sort of in the middle of the image, and the transformer, and just like all the different equipment that's inside of a substation. And you can kind of see there's like two big buses of wire. One of them is going horizontally and the other is going vertically towards the back of the page. And usually those buses are at different voltages. So the higher voltage bus will be typically higher up just to protect people from accidentally getting anywhere near it. And then the lower voltage bus will be a bit lower. And when I was on my first internship at Burns & McDonnell, it was pre-COVID, so we were able to be in person. And I was actually able to go out and visit a substation site. It was super cool. It's kind of hard to tell from the picture, but all of this, like if you're walking around it just like a normal height person, you won't be able to grab up and reach any of this stuff. Like it's all pretty high up, obviously to protect you. And it was interesting. When I was in the substation yard, I could actually feel like little prickles on my skin just because of how energized everything was. It's still safe and everything. It's just like, it's a lot of very high voltage equipment. And some of the equipment just makes buzzing noises constantly while it's operating. So definitely have to keep safety as your top priority when you're messing around with the substation, just because the voltages are so high. So now I'm going to move on to distribution. I just talked a little bit about substations, which are what changes the voltage from transmission level to distribution level. And so with power distribution, I talked about how transmission is like the major interstate highway system, whereas distribution is more like your neighborhood roads or your smaller roads that get you to individual houses. So it's like larger scale, and we're kind of zooming in more now. And with distribution, you have a lot lower voltage. I know I said earlier that the voltage you pull out of your wall just to plug in like your lamp and your computer charger and all of that, that's just going to be 120 volts. So we're going from, in the most extreme example, like 635 kV for transmission all the way down to 120 for distribution. So a really big jump there. And because the voltage is so low, we try to minimize the distance over which our distribution lines are spanning, just because there's a lot more loss when the voltage is so low. There's actually two types of distribution, primary and secondary distribution. You can see that on those two images on the right, those just show typical distribution lines. And the primary distribution, the primary lines are sort of on the top and the secondary lines are on the bottom, just in both images. And those things on the line to the left that look like little cans, those are actually transformers that step from primary to secondary. And again, we're just trying to minimize losses by keeping the voltage high for as long as possible because of that mathematical relationship I talked about earlier. So yeah, power distribution is what gets you to homes and businesses. So yeah, like I said, you definitely do not want to be having 700 kV coming directly into your house. That would, if you try to plug something into that, that would definitely cause a fire and burn up everything, and it would not be good. So yeah, we need to have a more manageable voltage because that's what all of our appliances and equipment are designed to handle. And so now that I've talked about the major steps in power generation, transmission, and then we're stepping it down with the substation and talking more about distribution, I want to talk about what the power grid in the United States looks like, a very high level overview again. So the American power grid is actually composed of three interconnects. You have the Eastern Interconnect, which is most of the Eastern United States, then the Western Interconnect, which is the Western United States, and the Texas Interconnect, which is the majority of the state of Texas. So yeah, those three grids, it's interesting because even though it spans a very large geographic area, the three phases of power that are produced by the AC sinusoids are actually exactly synchronized at 60 hertz on each of those major sections. So whether you're in Maine or Kansas or just wherever, it's always going to be exactly synchronized within that same connection. And there's been some discussion about whether we should try to merge these interconnects to have a more robust and resilient power grid. But unfortunately, that does not look like it's going to be able to happen in the near future, just because that would be a major large-scale project. Lots of money would need to be pumped into infrastructure for that to be able to happen. And the image on the right shows how power is marketed in different states. So the two main ways of regulating power being sold to consumers are traditionally regulated markets. That's essentially just an electric utility. Like if you live in a certain area, you just have your utility provider. That's just it. That's the way it is. That's the only person you're probably going to be getting power from, unless you're part of an electric co-op, which I can talk about later. And then you have some states, which are the ones in blue, it actually has a competitive market. So different power companies are going to be competing for your business. So I'm actually from Kansas City. So when I moved to Ohio for college and learned that for off-campus housing, you have to like choose your power provider, it just seems super weird to me because I was never used to hearing anyone talk about that, because we just have Evergy in Kansas as our power provider, and that's just how it is. But then in Ohio, that's one of the reasons why you have to choose who sells you power. And from a renewable energy perspective, it's interesting because the utilities in those gray traditionally regulated states, they own a lot of the renewable projects. So it sometimes can be difficult because utilities tend to be a little bit slower moving to get those projects off the ground. But then in those competitive states, it's more up to the individual company what type of renewable project they would like to do. So it also has ramifications, not only economically, but also environmentally. So now I'm going to talk just a little bit about careers in power engineering. I know it's very understandable. It's mostly, when you hear power engineering, you think electrical engineer, like that's the main like major that's going to go into power engineering, which is true. I mean, electrical engineers do have a lot of responsibilities in power engineering in generation, transmission, and distribution. So as an electrical engineering student, I can just talk briefly to what I did in my internships with Burns and McDonnell. So when I was in the substation department, I did a lot of work with routing cable and conduit throughout substations just to make sure those electrical connections between elements are strong. We also had people on my team doing what was called protection and controls. So they were essentially designing the substation to be resilient against any type of fault like I talked about, because if you have a fault in a substation and, for example, a transformer blows up, not only is the power company losing money, but you're also going to have power outages, which you certainly want to avoid. And then my second summer with Burns and McDonnell, I was working virtually and I did a lot of work with telecommunications. So inside control houses of the substation, there's a lot of routers that just transmit data back and forth to different substations. And I was trying to make sure that all of the correct routers were installed and like everything was up to date and could be serviced if it went wrong. And the reason why that communication between substations is so important is that that's actually a major way that power outages are prevented. So if a substation is feeding data that indicates an outage, the grid is smart enough in some places to be able to route power to a different substation to service those same sites. That's what's known as grid redundancy. So if one site goes out, you can still get power to the consumers without any outages. So yeah, that's definitely a very important part of power engineering. And that can also fall a bit more on the computer engineering side in addition to electrical. Now, it's also important to realize, so I talked a little bit about electrical. Now, civil engineers also can play a large role in all three phases of the power distribution, generation, transmission, and distribution. So when I worked at Burns and McDonnell, I had civil engineers on my team both years. They were they were learning a bit about like which types of concrete would be best to put the foundations for substation elements. That was their main focus in substation. And in generation and distribution, they do a lot with making sure that the plants are like following all the regulations they need to be and just building like the structures of the plants. And then with distribution, again, they're just pouring concrete and making sure that everything is up to speed with the lines. And mechanical engineers definitely focus more on the generation side. They can be working within power plants. And environmental engineers are very critical in all three phases just because power engineers have the potential to do a lot of environmental damage. So it's really important to be sure that those regulations are actually being followed. And then chemical engineers, again, mostly focus on the generation side. They do a lot of work inside power plants, just like trying to optimize the processes and that sort of thing. So yeah, with that, those are just the references I use in this presentation. So hopefully this session was informative and taught you more about the power grid, because I think it's personally very important to me just because I know it's something we all rely on. You can't, like, you would have massive power outages all the time if people weren't constantly making sure the grid was up to speed. So definitely important to know just kind of the basics of how it works. And if anybody has any questions, definitely feel free to ask in the chat or unmute yourself and say them.